Hi and welcome back to another LeetCode video. Today we're looking at LeetCode 3242, Design Neighbor Sum Service. Easy problem, and we're going to use this problem for our interview preparation, meaning this is not an explainer video, this is more an interview process practice video. Right, so what do we need to do? Well, we are given an n by n 2D array grid containing distinct elements in the range from 0 to n squared minus 1. Implement the neighbor sum class. Neighbor sum initializes the object. Okay, so we have a class here, we have a constructor, and we need to implement two functions. Int adjacent sum returns the sum of the elements which are adjacent to the neighbor of value. That is either to the top, left, right, or bottom of the value in the grid. The second function, diagonal sum, returns the sum of the elements which are diagonal neighbors of value. That is either to the top, left, top right, bottom left, or bottom right of value in the grid. So what I want to know is whether our grid can be empty and how large is it going to be. Is it it's always going to be square, but let's see. So we have at least 3 numbers in the grid. Okay, so that means there's always a way to compute the sum. But what happens when we compute the sum of a corner element? Well, I guess we just ignore the fact that we don't have elements neighboring here to the top and to the right. And the values are in the range from 0 to n squared minus 1. And at most, 2 times n squared calls will be made. All right. Cool. So I would say, I think we just initialize the grid in the constructor. We just copy whatever the grid is. And then when we call a method, computing the neighboring sum is going to be an O of 1 operation. So I don't think we have to do any pre-computing of any sums whatsoever, because we have to look at the finite number of neighbors and then get the value at those cells to sum them up to the sum. So I think the solution, even without looking at the examples, would be straightforward. But for the sake of completeness, let's have a look here. And yes, so we have a grid here. So this is the initialization. This is the adjacent sum of, no, wait, this is the initialization. Then we want the adjacent sum of the cell with the value 1. Right? And what is that sum? Well, 2. So that should be 6, right? So that's the value 6. Then you want the adjacent sum of the cell with the value 4. So that's going to be, well, 1 plus 3 plus 5 plus 7, which is 16. Yes. Then we take the diagonal sum at the same cell and we get the same sum. And all right, sorry, had an interruption here. So, and then we get the diagonal sum of the cell with the value 8. So I guess in terms of preprocessing, we actually do have to do something. We have to compute the position of a value. Otherwise, we won't be able to quickly find the neighbors of that cell. We don't want to seek in the grid to find the value of the cell of which we want to calculate the adjacent sum or diagonal sum or whatever. Cool. So yeah, so I think the initialization will be O of n times n time and space. And the 2 other functions are going to be O of n time and space. And I think with that we can implement it right away. So what we're going to do is we're going to, maybe we should determine what n is, right? And we should store that somewhere. So self.n is obviously the length of the grid. That is, the length of the grid is going to tell us how many rows there are, but because there are as many rows and as there are columns, we just need to extract that value once. And we're going to store the entire grid, or a reference to it as grid. And now we need to build up our index. And the index will be keyed based on the values. Like so. And I don't think But it doesn't tell us anything about whether it's going to make calls to cells that don't exist, right? So I don't know. But maybe since this is an easy problem, we probably don't have to deal with it, but let's keep that in mind for a second. So we're now going to iterate over all of the rows, right? And I like to use the variables x and y for that instead of r and c, as my other people like to do. So we just iterate over the rows with y in range n, and the same with the columns for x in range n as well. And now the value of at that position is going to be self.grid, or just at position x. So now we have to put that into our index. So we will say self.index at L. Maybe use a default dict for this. That will make things a little bit easier. Wait, let me clarify real quick whether all values are distinct. Yes, they are distinct. Okay, I don't think I'll use a default dict in that case because every value is going to be unique. So what we just have to do, valid index, that is basically the x and the y coordinate, of where. Cool. So that's all we need for the initialization, and we could simplify that a little bit like so. There's also a line of code. And so now let's look at adjacent sum first. So one thing that we have to take care of or be careful with is to check whether a position is actually a valid position on the board. If we want to get the neighbors of the cell with the value 0, then we're going to look left and up and so on. But we also have to check whether that cell even exists. Otherwise, we can't really access it. So what I would suggest is we create a little helper function. And that takes in the x and y position of a cell. And if x is smaller than n, or, oh sorry, smaller than 0, or x is larger or equal than self.n, well, we know that cell doesn't exist, so the value is going to be 0, right? It doesn't contribute to the sum. So we can just do that, and we will do the same for the y value. And otherwise, we're going to return self.grid at that position x, y. Right. So that solves the checking for us and isolates it into a little bit of code. So now the adjacent sum. Well, we have to look to the left, to the top, to the right, and below the cell. So, and the way that we can do that, well, we can compute the positions of the neighboring cells quite easily. So the position of the neighboring cell, I'm gonna use nx and ny as their coordinates, or in, and I like to combine that in a little zip function that iterates over 2 arrays. And what we'll have is, well, adjacent sum of value. So we will get our x and y from our index, right? And now we need to look to the right of x, so that's x minus 1, but we will keep y the same. Next, we look at x and at y minus 1, so that's looking at the cell above x and y. Then we look at x plus 1, and y stays the same, so that's now looking at the right position next to the cell. And finally, we keep x the same again, and we look at y plus 1, so that would be the cell below x. And well, and the sum is going to be 0 in the beginning, and I'm going to return it later. And in between, we're just going to add to the sum self.get value nx and y. So that is all we need to compute the adjacent sum of the cells. Now we have to do exactly the same thing for the diagonals, except now our coordinates are slightly different here, right? So we have to look at, maybe let's start from the beginning. We have to look at the top left corner maybe first, so that would be x minus 1 and y minus 1. Then maybe the top right corner, so that's x plus 1 and y plus 1. Then we look at the bottom right corner, so it's still x plus 1. Oh, sorry, I should have had x minus 1 here before. The top diagonals are always y minus 1, and the bottom ones are always y plus 1. And only the x values are alternating. Left, right, right, and so that covers all the diagonals from the cell. And we can use the get value function just as we did before. No other changes. And if I'm not mistaken, that should work quite well. So I'll just run now the test cases. In an actual interview, I would probably go through an example so that these things don't happen, you know. For y in range, n is not defined, right? Because we have to call it self.n, and I just add self here as well. Do I have any other mistakes like this? Here I have self.n. Here we don't care about any of that. Okay, so let's retry. Okay, so the test cases pass. Nice. And now we're going to submit it to see if it really passes all of the test cases. And it does. Happy times.